And there's several ways to employ randomness in a more intelligent way, but there's one that is actually quite common. So let's assume that this here is a huge list of all possible solutions. So for NP-complete problems or NP-hard problems, this will be an exponentially large list. And the strategy of more intelligent random algorithms, and we're soon going to see a concrete example for that, is basically to randomly pick out certain solutions here in this list. And let's say that the list is ordered in some way, which I'm going to explain in more detail when we get to the concrete example. And then the strategy is to explore solutions that lie around the ones that we randomly picked. So like this. So you would look at all of these solutions here, all of these solutions, something like this. Now, of course, each time the algorithm runs here, it can only investigate a number of solutions that is polynomial in size. Well, of course, the list of all potential solutions, so this whole thing here, has exponential size. And through the way in which you design this algorithm, well, first of all, you want to ensure that you land in good places, so to say. And this is often, of course, not very trivial to prove how to do that. And the other thing is that you want to have a good and intelligent exploration of the area around your solution. Again, something which is often not very easy to prove or show. Actually, we can't expect it to be any other way. After all, we're solving a very challenging, namely NP-hard or NP-complete problem here. So just to prepare you a little bit for the realities that you are about to face, let's do another quiz. Let's say we have a randomized algorithm for an NP-complete problem, and that algorithm has a fixed error probability. Say the algorithm makes an error with a 90% chance and only gives us the correct answer with 10% chance. So should we expect that a randomized algorithm for an NP-complete problem that has a fixed error probability, so say with 90% chance it gives us the wrong solution and with 10% it gives us the correct one, should we expect such an algorithm to run in polynomial time? And I'll give you three choices, and as always more than one can be true. The first choice I'm offering you is no, because if we would run that algorithm just a few times, we would almost be guaranteed a correct solution, even though this algorithm here that I'm asking you about makes an error with a 90% chance for each time that we run it. Or is the answer no, we should not expect that, because the number of potential solutions is exponential, and the algorithm, since it runs in polynomial time, can only, and this of course anthropomorphizes a bit, can only afford to check a small part of that exponential solution space, if you will. And finally, one choice I'm offering you is yes, we should expect that, because the laws of NP completeness that we have gotten to know in the past units do not account for randomness. So just as these laws don't account for small bases, or if we are content with an approximate solution, it could be that randomness makes such algorithms possible. So please check all of these here that you think are correct.